Our seventh lecture video will cover Bernoulli's principle. For any incompressible fluid, the volume rate of flow is the same past every point in a pipe or a stream. The speed of the fluid is faster where the pipe or the stream is more narrow, and it is slower where the pipe or stream is wider. Let's think about this visually. If we have a wider part of the tube, the cross-sectional area is greater. With a greater cross-sectional area, in order to have the same volume rate of flow, the fluid must be moving slower than if we have a smaller cross-sectional area, like in the center of the pipe, by A2. In order to keep the volume rate of flow constant in the middle here, the speed has to be much greater. The idea of volume rate of flow being the same past every point can be represented by the equation V1A1 equals V2A2. If V1 goes up, A1 must go down, assuming V2 and A2 are the same. Conversely, if V1 goes down, then A1 must go up in order to keep the same volume rate of flow. Another way you can think about this is if you have ever taken a hose outside and put your finger so that it partially covers the water coming out of the end. What happens to the water? It shoots out much faster. That is because the volume rate of flow has to stay constant, so if you are restricting the area, the speed has to increase. Bernoulli's principle tells us that for the horizontal fluid flow through a tube or pipe, the sum of the pressure and kinetic energy is the same at every point along the tube. What this means is if we have a wider part of the tube, like over here, the fluid will flow slower. If it is moving slower, then it will have less kinetic energy, because kinetic energy is dependent on the velocity. If there is less kinetic energy, then in order to have the sum of the pressure and kinetic energy the same at every point, there must be higher pressure. So in the wider part of the tube, there is less kinetic energy, but higher pressure, as we can see from the tube on the left side. If we look at the narrow part of the tube, the fluid is flowing faster. Since it is moving faster, it has more kinetic energy. Since it has more kinetic energy at a higher speed, the pressure at that point in the tube must be lower in order for the sum of the pressure and kinetic energy to remain constant. So in the narrow part of the tube, there is more kinetic energy but lower pressure, as represented by the tube on the left. Let's take a look at a few examples of Bernoulli's principle in practice. If we look at an airplane wing, the velocity of air above the wing is greater than below because it has a farther distance to travel in a given time. Since the velocity above the wing is greater, the kinetic energy is also greater. Since the kinetic energy is higher, the pressure must be lower above the wing. Below the wing, the air is moving slightly slower. Since it is moving slower, there is less kinetic energy. If there is less kinetic energy, the pressure below the wing is greater, which causes lift, since the pressure above the wing is less than below the wing. Another example of Bernoulli's principle is throwing a curveball. Let's say you throw the ball and it is rotating clockwise, like in this picture. On the top of the ball, the air is moving in the opposite direction as the ball is rotating. Underneath the ball, the air is moving in the same direction as the ball is rotating. The rotating baseball drags a layer of air immediately next to its surface. This reduces the speed of air at the top of the ball and increases the speed of air underneath the ball. On the top of the ball, because the speed of the air is reduced, there is less kinetic energy. Since there is less kinetic energy and the sum of pressure and kinetic energy has to remain constant, there is locally higher pressure above the ball. Conversely, underneath the ball, the speed of air is increased, so the kinetic energy is also increased. Because the kinetic energy is higher, the pressure must be lower. This locally lower pressure is what causes the ball to curve downward. This concludes our discussion of Bernoulli's principle and properties of fluids.